So today on AI Paperslop, we are jumping straight into a massive breakthrough in video generation. The paper is called Streaming Multi-Agent Autoregressive Diffusion Model with World State Registers.
Right, which is quite the mouthful, but they call the model WorldWeaver, or W squared. It's from researchers at UCLA and Adobe.
Yeah, and the core insight here, I mean, the reason you, the listener, need to pay attention to this is that it finally solves the lack of object permanence in these models.
Exactly, because usually multi-agent video models, they just rely on local KV caches, right? Like just the memory of past frames to infer the shared world.
Which is terrible for consistency.
Hmm.
But WorldWeaver fixes this by introducing what they call World State Registers, or WSR. They're these learnable tokens that act as a persistent, dynamically updating memory of the global environment.
Yeah, and by separating the visual rendering from the actual state tracking using this really clever mixture of transformers architecture, they train it across 3 specific stages.
And the results are insane. The baseline world consistency score jumps from an 81.0 to a staggering 105.1.
It's a huge leap.
It really is. So our mission for this deep dive is to unpack exactly how these registers are trained, right?
Yeah.
Like what kind of supervision signals stop them from just drifting into noise over long generations?
Yeah.
And why the mixture of transformers backbone is critical here.
Right, because to really appreciate the elegance of decoupling state from vision, we have to look at the specific mechanical failure of current autoregressive video models.
Like Solaris, for example.
Yeah, like Solaris. So in standard chunk-based generation, the model predicts a chunk of frames, right? Then it carries its observation history forward using causal attention and KV caching.
Standard stuff.
Exactly. But the fundamental bottleneck is the decoding process. Because the network forces everything into pixel space at every chunk, it has to repeatedly re-infer the entire hidden 3D world state.
From just a highly restricted, like, biased window of recent 2D observations.
Yeah, it's looking at a flat picture and trying to hallucinate the hidden geometry behind it, frame after frame, over and over again.
Which, I mean, if you've ever tried to build a continuous simulation, you know the exact pain point this creates.
Mm-hmm.
It's basically the equivalent of trying to manage a complex multiplayer video game using only local variables.
Oh, that's a great analogy, yeah.
Right? Instead of a global state variable tracking where all the players and items are on the map, you're like forcing the rendering engine to look at the last 5 frames drawn on the screen and deduce where everything should be next.
Which is just mathematically fragile. You hit what's known as the multi-view dilemma.
Right, where if Agent A looks away from a structure and Agent B also turns away, the visual evidence of that structure just falls out of the sliding window of the local KV cache.
Exactly. The self-attention matrix physically has no tokens representing the occluded object. So the model develops a severe amnesia. When the agents look back, the structure is just gone.
It's vanished. So the structural fix that WorldWeaver introduces, it addresses that amnesia at the sequence level.
Wait.
Okay?
Right. Instead of feeding the transformer a pure sequence of frame tokens, they explicitly interleave frame tokens with register tokens.
So it looks like what? Frame X0, then register R0?
Yeah, exactly. Context from X0, then register R0, then X1, R1, and so on. This specific ordering makes the rollout causal at the state level.
Oh, I see. So the register is permanently wedged between the frames in the pipeline.
Right. So when the model generates a query to update register RI, it attends to the local context frames within its sliding window, say xi minus w plus 1 up to xi.
But it also attends to the immediately preceding register Ri minus 1.
Exactly. It's carrying forward a compressed representation of the world that exists completely independent of the pixels. The register updates dynamically as new frames arrive, pulling cross-agent info into this centralized memory bank.
It really is just a global state variable.
It is. But inserting learnable tokens into a sequence doesn't just magically grant them spatial awareness.
Right. I mean, if they only get a diffusion loss signal during training, which is just trying to denoise pixels, the network has no idea what it's actually supposed to store in them.
Yeah, it would probably just take the path of least resistance, like use the registers to memorize local texture patches or color gradients just to make the immediate denoising task easier.
So to force them to learn actual physics and geometry, you have to ground them.
Exactly. And the researchers achieved that grounding with 3 explicit supervision heads during training. And a really critical detail for the ML engineers listening down, like these heads are discarded entirely during inference.
Oh, wow. So you get all the benefits of the dense representation with 0 compute overhead at runtime.
Yep, which is absolutely vital for a streaming model. So the first of these signals is agent status, which focuses on local dynamics.
Meaning it predicts a simulator state vector, right?
Right, for each agent in the scene. So it has to predict their exact position, velocity, and orientation in the 3D space. That mathematically grounds the agents.
Makes sense. And then the second signal tackles the global geometry, which they call the bird's eye view target.
Yeah, this is an allocentric top-down view of the world. But instead of predicting raw overhead pixels, the head targets a 16 by 16 grid of 768-dimensional Dino V2 ViT B14 patch features.
Wait, Dino V2? That is a heavy feature space.
It is, but Dino V2 features are uniquely suited for this. They explicitly encode dense part-hole relationships and depth boundaries, so predicting this feature map forces the register to maintain a highly structured 3D spatial map of the environment.
Even for areas that are currently occluded from the agent's direct view.
Exactly. And then the third signal introduces cross-modal semantics through scene text. The register has to predict textual scene descriptions.
And they used a frozen Llama 3.21b model as a scorer here, right?
Yeah, and the training text was heavily annotated offline using a vision language model, specifically Qwen 2.5 VL.
But wait, this brings up a massive technical challenge regarding network capacity.
Oh, absolutely.
Because, think about it. If we're using a diffusion loss to generate continuous video pixels, but simultaneously demanding that the exact same network predict discrete language text logits and 768-dimensional Dino V2 features,
Yeah.
aren't we just setting up a catastrophic parameter conflict?
Yeah, you are.
I mean, pixels, text, dense spatial features, they require fundamentally different latent representations. If you force them through the same linear layers, it usually just destroys the gradients.
That is the exact pushback you should have, and it's exactly what the researchers saw. When they tested a standard dense transformer with these competing objectives, the model just collapsed.
We couldn't handle it.
No, it collapsed under the weight of the conflicting representations. And this failure is what directly motivates the next major architectural evolution in the paper, the mixture of transformers, or OMOT.
Right, because you can't just throw more parameters at a dense model if the gradients are actively fighting each other.
Exactly. The MUTI design implements strict routing to isolate the computation. The register tokens and the content frame tokens are routed through entirely separate modality-specific weight branches.
So you have a dedicated state branch for the registers and a visual branch for the frames.
Yes. They maintain separate projection layers, separate feed-forward networks, and separate normalization layers.
But they still share attention, right?
Crucially, yes. While their processing layers are isolated, they share the self-attention mechanism, so they can still talk to each other and share context across the sequence. The visual features inform the state, and the state guides the visual generation.
They interact continuously, but they don't overwrite each other's specialized logic. And the data really proves how necessary this isolation is.
Oh, the ablation studies are wild.
Yeah. Training this model without explicit text supervision, a dense model gets a 95.5 world score. And the MUTI architecture actually drops slightly to a 93.8.
Right, because the routing overhead of the MOTI isn't justified by the complexity of the representations at that baseline level.
But the moment you introduce the scene text supervision, demanding that the model align its world state with language semantics, the dense model crashes down to a 91.3. It physically cannot balance the modalities.
But the MOTI architecture skyrockets to a 103.2.
That's crazy.
It tells us something fundamental about scaling multimodal architectures. Richer semantic representations like language-grounded world states, they just cannot be processed with the same parameterization as local visual tokens without severe interference.
You have to isolate the heavy computation while preserving the communication pathways. Okay, so we have the world state registers solving the memory bottleneck, we have the 3 supervision targets grounding the physics, and we have the MOTI architecture preventing parameter collapse.
Right.
But how do you actually train a streaming autoregressive model so it doesn't just hallucinate itself into a corner during a 1,000-frame rollout?
Yeah, that requires a highly specific 3-stage training curriculum to overcome error drift.
Right. Stage 1 is bidirectional training, I think, for 120,000 steps.
Correct. They initialize from a single-player baseline model and fine-tune a multiplayer teacher. In this first stage, the model gets full temporal context. It can look forward and backward in time.
So it's basically a God's eye view.
Exactly. This bidirectional attention lets the network learn the synchronized cross-player structure of the data understanding shared layouts and relative player motion by seeing the complete trajectory of the environment.
It builds a perfect teacher model.
Mm.
But obviously, for inference, the training wheels have to come off.
Right. Stage 2 shifts to causal training with the world state registers for 80,000 steps. The bidirectional teacher is converted into a causal student.
So now it's forced to predict the next frame, looking only at the past.
Yeah, applying a flow matching objective combined with the 3 explicit register supervision targets. And the shift to a flow matching objective here is a really important departure from standard diffusion.
Because it's smoother.
Way smoother. Traditional diffusion predicts random noise steps, but flow matching learns a direct vector field. It draws a much straighter optimal transport line between the noise and the target distribution.
Which makes sense, because when you're generating hundreds of frames autoregressively, standard diffusion paths can get extremely jittery.
Unstable, yeah. Flow matching smooths that trajectory out.
Okay, but this still leaves us with the classic training versus inference mismatch, right?
How so?
Well, during stage 2, which relies heavily on teacher forcing, the model is fed ground truth past frames. It operates with a safety net. But in the real world, during inference, there is no ground truth.
Right, it has to eat its own outputs.
Exactly. If it makes a tiny mistake and generates a frame with a slight geometric error, that flawed frame goes directly into the KV cache. The next frame builds on that error, and without correction, it just warps. The video degrades into a hallucinatory mess.
Yeah, error accumulation, which is exactly what stage 3 is engineered to prevent. It utilizes self-forcing with rollout for a brief but critical stretch of about 3,000 to 4,000 steps.
Okay, so the student model rolls out its own generated context, basically making its own mistakes.
Right. And then the researchers apply fresh noise to that imperfect rollout and use distribution matching distillation, or DMD, to correct the trajectory.
And DMD compares the noisy generation against 2 different models, doesn't it?
Yeah.
A frozen score network initialized from that perfect stage 1 teacher, and a tradable critic that evaluates the student's outputs.
Yes. It constantly aligns the distribution of the student's messy autoregressive errors back to the perfect teacher distribution. But during this stage 3 phase, they discovered a fascinating quirk in the loss landscape.
Oh, right, the convergence issue.
Yeah, they noticed the register loss was converging much slower than the DMD distillation loss. The pixel representation was stabilizing, but the spatial representation was lagging way behind.
Which makes total sense when you think about the gradients. I mean, denoising local pixels is a much cheaper mathematical lesson for the network.
Exactly.
Establishing consistent spatial geometry requires complex global reasoning. If you keep updating both branches at the same time, the visual branch just overfits to the noise while the registers are still struggling to lock in the harder physics.
So to solve this, they implemented this brilliant MOT hack. Because the visual and state parameters are structurally separate, after step 1500 in stage 3, they completely freeze the visual transformer.
Just totally lock it down.
Yeah, they stop updating the pixel rendering weights entirely and channel all the optimization into the register transformer,
Forcing all the network's remaining compute entirely into mastering the state representation. And the metrics prove it works. By locking those visual weights, the vision language model accuracy, which is how they measure the logical consistency of the generated video, it jumped from 63.8 to 68.1 in that final stretch alone.
It's a huge boost.
It is. And the overall metrics across the board validate the entire pipeline. I mean, comparing WorldWeavers against the Solaris baseline, the overall world score increased from 81.0 to 105.1. Building accuracy, the model's ability to depict players building structures without the blocks spontaneously disappearing, that went from 9.4% to 28.1%.
That's a massive difference in object permanence.
And overall consistency climbed from 57.8% to 76.6%. This explicit modeling isn't just like generating pretty pixels, it is maintaining a verifiable state engine.
But, this does raise a practical hurdle for scaling this architecture to the real world.
Right, the data dependency.
Yeah, the training for WorldWeaver relied heavily on perfectly logged game engine data. An environment like Minecraft gives you flawless agent coordinates and perfect bird's eye views.
But if you are scraping autonomous driving footage or just random video data, you don't have perfectly logged overhead views for every single frame.
Yep.
You can't just extract dense Dino V2 features or precise 3D coordinates out of thin air for unannotated video.
Exactly. So to prove this architecture scales beyond synthetic game data, the paper simulated a proxy for the real world by stripping away the labels. They trained the model using only 1,000 labeled bird's eye view clips alongside 10,000 completely unlabeled clips.
So a 1 to 10 ratio.
Yeah. The labeled samples received the flow matching loss and all the register supervision losses, while the unlabeled samples only trained the video generator through the standard objective.
And how did it do?
Well, even with 90% of the data missing those dense geometric targets, the world score still hit a highly impressive 90.3.
Wow, okay. So the registers can successfully anchor hidden world states, even when the vast majority of the training data is just raw video.
Exactly. As long as the network has a small, high-quality supervised subset to teach the registers how to behave geometrically, they will continue to apply that latent logic to the unlabeled data.
Which means WorldWeaver completely redefines memory in autoregressive video diffusion. By moving away from treating memory as just the pixel features sitting in the KV cache, and instead treating the world state as a separate, explicitly grounded entity, it finally gives generative models true object permanence.
It's a dedicated neural scratch pad to track the geometry of the scene independent of the camera view. And, it really makes you wonder if learnable registers can maintain multi-agent geometric consistency using synthetic top-down views. What happens when we apply this to self-driving car data?
Oh, that's interesting.
Right. Could we use these explicitly grounded registers not just for generating predictive video, but as actual queryable decision-making representations for embodied AI? Imagine an autonomous vehicle acting in an unconstrained, multi-agent environment where its internal world model is actively maintaining a persistent geometric register of every pedestrian and vehicle, even when they are completely occluded behind a building or a truck.
Taking that a step further, if we can run a persistent logical geometry engine purely in the latent space of a generative model, it begs the question of whether the future of robotics needs external physics engines at all.
Exactly.
Could a robot simply imagine its physical limitations and the state of the world around it with total consistency before it ever even moves an actuator? It is a massive step toward true world models. Something for you to definitely mull over. Thank you for joining us for another breakdown on AI Paper Slop, your definitive source for the latest technical AI research. We will catch you on the next one.